in here. Get the period. That's Brian. He's the math guy.
Got it all here.
Alright. Should probably go over there.
Count down from 3.
Alright. 3. On go. 3, 2, 1, go.
Alright, we gotta do it 3 times. We can count. 3, 2, 1, go.
Oh, okay.
Wait, what was that first one?
From their back, right?
Yeah.
2.3.
Okay.
2.3. Alright.
Ready?
Alright, 3, 2, 1, go. 2.2.
Alright. Is AF autofocus?
I don't know. Yeah, I think so.
I guess. That's dope.
3, 2, 1, go. 2.28.
Alright.
Awesome. Alright, so now we're measuring the angle of our pendulum right here. And what do we got? We got 40 degrees. 40 degrees. Yeah. 40 degrees. 40 degrees. Alright, so we're going to measure the string right now. Let's attach this mess. Because we need to know some length. And that is 52 and a half. So that's in inches, but we'll convert it to some meter, guys.
Okay, so here's our first experiment we did with the pendulum. Our purpose is energy conserved in a pendulum, so basically we're trying to figure out that is the potential energy at the top of the pendulum's oscillation equal to the kinetic energy at the bottom. So first we took all of our measurements, and to find the height we did the length of the string on the pendulum subtracted by the length of the length times the cosine of the angle, which would equal the height, and we got 0.31 meters for the height. And using P equals mgh, we found the potential energy when it's at that height to be 3.062 joules. So then we found the velocity using this equation, and we found that it was 2.475 meters per second, which was its maximum at the bottom. And then plugging that into the equation Ke equals 1/2 mv squared, we found out what the kinetic energy was, and we saw that it was very, very close to the potential energy, which showed us that yes, it is conserved, and we had a percent error of 0% because we're perfect. Yeah, awesome.
Alright, 3, 2, 1, go. 1.6.
I feel like I'm in NASCAR.
3, 2, 1, go. 1.48.
Gonna do another Tommy trial, Brendan. Hey.
Alright, ready?
Yeah.
3, 2, 1, go.
What's the time?
1.45.
Ooh, 1.45.
Okay, so for our second experiment, we were solving for the kinetic coefficient of a steel ball on wood using energy. So this is our procedure, where we found the distance, velocity, height, and the measured angle, which was 17 degrees. First we used potential energy equals kinetic energy, final minus work final. And from there we got mgh equals 1/2 mv squared plus 1/2 iw squared minus friction force times the distance. From there we looked at what we were given, so the mass was 0.536 kilograms, their height, initial velocity, acceleration, distance, measured angle 17 degrees, time, and we needed to find the final velocity. To find the final velocity, we used VF equals VI plus AT, plugged in what we knew, and since the initial velocity was 0, as our final velocity, we got 4.331 meters per second. To find work, we use the first equation that we used, and we got 7.27 joules. And using the work, we did force times distance, and friction force equals coefficient times the normal force, and solving for the coefficient, we got 0.65.
Yeah. Alright, so now we're checking to see what the equilibrium point is, and I would say that's at about 60. Alright? Yeah. Whenever you're ready. Hold up. It's not straight. Okay. Alright, ready? Yeah. Nice noises. Alright. So now let's rewatch the footage. What is it looking like?
It's half on my phone. 30 to 80, about.
So it goes, the top is at 30, the bottom's at 80?
Yeah.
Okay.
I mean, you could relook at it again. Like, I tried it because it was hard.
Okay, so this is our third experiment in a spring, and we want to know if the energy is conserved. So there's our little diagram. The mass is 2 kilograms. So we wrote that down for a given. X initial is 0.6 meters. The max is 0.8 meters. Minimum 0.4 meters, which was all collected by Brian Welsh and the rest of the group himself. We have the length of the spring is 0.174 meters without the mass on it, and the length of the spring is 0.45 meters when the mass is on it, so that's change in X, 0.276 meters. Using the formula F equals negative K X, we were able to plug in whatever we had up there and get 35.543 Newton meters for K. Then using the formula V equals A square root K over N, we were able to again plug in the numbers that we found, and we were able to get negative 1.192 meters per second for the maximum velocity. We then used the potential energy equation, which is 1/2 kx squared. Again, we plugged in the numbers we found, and we got the potential energy to be 0.7109 joules. And then we also did the same for the kinetic energy formula, plugged in what we knew, and we got 0.7109 joules. So obviously that's the same. So our question was, does potential energy equals kinetic energy? And it is shown that the 0.7109 equals 0.7109, so yes, energy is conserved, and for our percent error, it was 0 because we got the same number. Adios.
Yo, try one.